Okay, so I want to start supporting something for EVEX called compressed 8-bit displacements. And this is basically just like an optimization that they put in for EVEX specifically, so that when you do an 8-bit displacement, you can basically give it a number to multiply a scaling factor by to get the displacement that you want. So if we look at the example of this encoding table here, this doesn't affect legacy encoded instructions, and it doesn't affect VEX encoded instructions at all. So if we look at these, this is operand encoding A, and this one is B. A and B don't have this thing called a tuple type, but the EVEX instructions here, which are all C, they all have the tuple type full. And so probably this tuple type only applies really to deciding whether you're going to encode a memory access displacement as 8-bit displacement or not. So probably the easiest thing to do is to show like an example. So if we just go and create a test file, we'll call this EVEX compressed disp8 .asm. So I'm on the add PS instruction right now. So we do xmm 0, xmm 1, and then some memory access. But I want to force EVEX encoding here, so I'll just use an op mask here. This has nothing to do with the displacement, it's just to force the EVEX encoding. And we'll have one more that is just VEX encoding, maybe. So we'll do the same thing in both of these. We'll say RCX and RCX as a memory access. So let's just go and generate listings for these. So this is EVEX, and then we're going to have EVEX LST. Then we've got EVEX LST. Let's just go and look at the listings. So these are being encoded as you would expect. This has the VEX prefix. This has the EVEX prefix. And then they basically just go through their prefix bytes until they get to the opcode. And then they have a mod RM to select the operands. But if we add a displacement to each of these, so let's say we add, I'm going to use 16, which I'll explain in a minute for both of these, but I'm going to use 16 multiplied by, let's say multiplied by 127. Okay, so let's generate these again. Okay, so now if we look at this, this is the normal memory access with no displacement, so there's no difference in these two. Then there are these ones with the memory displacement, and so you can see the VEX one here has been forced into a 32-bit displacement because the number is too big for an 8-bit displacement, but the EVEX one is actually only outputting, so we've got the opcode here, we've got the mod RM, and then we have only 1 byte of displacement here. And this 1 byte here, as you can see, is 7F, which is, this is basically 127. So the multiply that I did here by 127 is being encoded as the 8-bit displacement. So in EVEX, when you use an 8-bit displacement, it multiplies the 8-bit displacement that you've encoded by some scale to get the original displacement that you wanted. So in this case, you could see that the scale was 16, so it multiplied this by 16 to get 2032. But how you know what the scale is all depending on the tuple type. So the tuple type for this encoding was called full. And what full means is that it means that in a normal memory access with a displacement, full means use the full number of bytes for the vector length. So in this case, we've got XMM, which is 128 bits, which is 16 bytes. So in this case, full as the tuple type is telling us that n, which is the scale for compressed disp8, is going to equal 16. Which is why I knew that I could use 16 here. So what happens is that it says, well, this number is divisible by 16, and if I take this number and divide it by 16, then I get 127. 127 fits within a single byte, therefore I can use compressed disp8 displacement encoding. If I copy this and do 16 multiplied by 128 and regenerate the listing, now we can see that for this second one, it's been forced into disp32 instead, because this no longer fits within a signed byte anymore. The 128 no longer fits within a signed byte anymore, so it can't use disp8 compressed encoding. Therefore, it is forced to just output this number as the raw displacement in a 32-bit displacement here. So it's a bit confusing to see what's going on, but basically EVEX gives you this compressed disp8 encoding, which is that if you can figure out what the n scale is for this particular operand encoding, and you can find a number that fits within one signed byte to multiply the scale by to get your original displacement, then you can use 8-bit displacement encoding and put that number into the displacement. And then when it executes, it will multiply that number by n to get your original displacement. If you can't do that, so if it's not divisible, if your displacement is not divisible by n, or the compressed displacement that you would multiply n by doesn't fit within a byte, then you cannot use disp8 encoding, and you must use 32-bit displacement encoding instead. So the rule for this is basically that you have a displacement d. You have a displacement d. If d mod n, which in this case was 16, is 0, then you can try to use disp8 compressed encoding. Otherwise, you have to use 32-bit displacements with the raw displacement output. If it is divisible, you then get the compressed displacement, which is the number that you multiply n by. So to find the compressed displacement, you just do d divided by n. And if this fits within a byte, then you can output it as a disp8. That's all there is, really, to encoding compressed disp8 memory displacements. The main trouble is figuring out what n is for any instruction. So to show what n is, we'll just go and look at the tables. So it's all dependent on this tuple type here, and full told me that for this particular instruction, n was going to be 16. It also tells me that for YMM it's going to be 32, and for ZMM it's going to be 64. So if we go to the AVX 512 and EVEX prefixes section of the manual, they have a table down here where they describe what all of these tuple types mean. So here we can see full and half, and then these are split into two different tables. And that's because when you're using the tuple types to figure out n, these top two here, n changes if you're using a broadcast. For all of the other ones down here, the broadcast doesn't matter at all. So if it's full, as it was with add PS, then with no broadcast, like in my example, n is just whatever vector length you're using. So if you're using XMM, then it's 16. If you're using YMM, then it's 32. If you're using ZMM, then it's 64. If you are using a broadcast, then the n is basically the input size, which is the element size within the vector. So for PS instructions, which are packed single precision values, a single precision value is a 32-bit float. So 32 bits here is 4 bytes, which is why they are all 4 here, if you're using a broadcast. If you were using PD, then they would be 64-bit floats, which are 8 bytes each. So in the case of using a broadcast, n is always 8. When you don't use when you don't use one of these tuple types, when an operand encoding says that it's not one of these tuple types, so it's any of the other ones down here, broadcast doesn't change anything. Instead, it's just the numbers here. So full memory is just saying that you use the n is just the number of bytes in the vector length. Then down here you can see half memory, which as you can probably guess is just full memory divided by 2. So you get 16 goes to 8, quarter memory goes to 4, so divided by 4, you know. And then down here I think there's 8th mem as well. So these memory ones basically just use the vector length, and then if it's half you divide by 2, if it's quarter you divide by 4 to get, or if it's eighth you divide by 8 to get the n. In the case of tuple, so tuple 1 scalar here is basically saying the element size, so this is where it's looking at input size again. So tuple 1 scalar is that if you're, for example, using 32-bit floats, they're 32 bits, therefore n is always 4. If you're using 64-bit floats, then n is always 8. Same for fixed down here. If your input size is 8 bytes, then n is 8 bytes, or if your input is 4 bytes, then n is 4 bytes. In the case of these other tuple ones here, tuple 2, tuple 4, and tuple 8, all you do is find the tuple 1 size and multiply it by the number. So here, if you're using 32-bit, then it's 4. Well, tuple 2 is just 4 multiplied by 2, so you get 8. Tuple 4 is multiplied by 4. In this case, there isn't... you wouldn't find tuple 4 for this particular vector size. But in the case of this one, so, if we're using 4 byte elements, you get 4, multiplied by 2 is 8, and then multiplied by 4 here is 16. So that's how that works. And then down on the next page here, you can see there's a couple of extra tuple types. Mem 128 is always 16. And then this mov dedup here is like a special case where it's 32 and 64 for these two vector lengths here, but the XMM vector length is like an 8 instead of a 16. So basically, all I need to do is to implement this is tell each form what its tuple type is, and then for tuple types that need an element size, which is basically any tuple type that's not full memory. In those cases, I also tell the form what the element size is as well, and then I can do the calculations in the encoder to figure out whether I can use compressed Disp8 or whether I need to use 32-bit displacements. So let's go back to add PS again. and we'll create some tests for this first. So I'll get rid of these normal ones up here. We just want to focus only on EVEX right now, because this is for this compressed Disp8. So basically what I want to do is test, for example, so this one is saying that the tuple type is full, which means that it's going to be, n is going to be the number of bytes in the vector length. So in this case, xmm is 16, so we'll do 16 as the displacement. That means the displacement should be encoded as 1, because 1 multiplied by 16 is 16, and therefore it can be encoded as compressed Disp8. We'll also do another one where we don't have a divisible displacement. This one should force Disp32 output. And then we'll do a couple that just go right up to the edge. So we have multiplied by 127. And then we have 16 multiplied by 128. So this one should be Disp32, but this one should be Disp8. For the other ones, I think also maybe I'll keep a negative one in here as well. Now for the other tests, I'm going to get rid of these sort of like limit ones, because I think this will be enough to test the limits of it. So next we'll use YMM, and the full n for this will be 32. So we'll do 32 for these, and we'll do 33 for this one. And then we need to do ZMM, where the n will equal 64, and in this case it will be 65 to force the Disp32. So that's the add PS like test cases. Another instruction to test will be, for example, well, let's also do we need to also do broadcasts for PS actually, now that I think about it. So we'll copy all of these ones, and we'll put a broadcast on. So broadcast for this will be 1 to 4, I think. Then the broadcast for this one, oh, I need to copy these. This is 1 to 8. Then I need a copy of these ones, where we'll do a broadcast for 1 to 16. Because with the full tuple type, the broadcast changes the n. So n becomes the element size, which for PS is 4 for every single one of these broadcast cases. Then we'll take another test, which will be, instead of add PS, we'll do add PD, just to check that the element size is being used correctly. And then we'll move on to some other tests. So another one is, for example, MOV SS. So this one has a tuple type of tuple1 scalar, and it's only F and G that I need to do here. So they're both XMM, and actually I'll probably just do one of them. I'll just do this one here, because they're both M32, and the displacement logic is going to be the same in either form. So we'll just do this one. So if we've got MOV SS, oh, this will be VMOV SS. And then we'll do XMM 0, and then we'll have some memory access. Maybe I'll do K1 on here just to force EVEX. And then memory access can just be RCX plus. And then this is saying tuple1, so this is the element size, or the input size. So the input size for this is 32. So we should do, for example, 4 here, because the element is 4 bytes. So if we do 4, then that means that the compressed Disp8 should be output as 1. And then if we do 5, it should force a Disp32 output. Then we'll just take this, and these ones don't do broadcast actually, so I don't need to do that. So that should give me an okay enough test for that. These are only XMM. Then finally, I'll also test, let's say, MOV DQU8. So these ones have full mem. So not just full, it's full mem instead. And full mem is not affected by broadcast. I don't think that you can actually do broadcast on any of these anyway. So we'll basically just take, for example, we'll do maybe C or something. So we've got XMM, YMM, and ZMM. So we'll take these. So we've got XMM. These ones are VMOV DQU8. So we've got a vector register followed by a memory access. So in this case, it's saying that it's full mem, which means that for XMM, it's going to be 16, and we'll do 17 for the other test. Then we'll do YMM, in this case 32 and 33, and then here we'll do ZMM with 64 and 65. Oh, mismatch in the number of elements. That's because I changed these ones to PD, but then I didn't halve the broadcast elements. Okay, so let's have a look at the listing for this. We can see that, for example, this one here is being forced to use 32-bit displacement. This one is so this one's being using 32-bit displacement because n has changed for this. N is now 4 instead of 16 for this one. So I'll go and just change these ones a little bit. So this is now going to be 4 multiplied by 127. And this one's going to be 4 multiplied by 128. Then we've got the same thing for PD down here, but this one is going to be, let's see, we've got, this one is still the same because this will be using the full vector length, but this one's going to be using the element length, which is now 8 for this one, multiplied by 127. And this one will be 8 multiplied by 128. And I think that's all of those done. So let's just go and check now. Okay, so now the broadcast is correctly using compressed Disp8 for this case, but 32 for this case. And let's just check that the other one is okay. That's also using 1 byte, so that's fine. Okay, so I think that all of the tests are okay there, for the NASM file at least. So now I need to create some tests for these in the Go file. And actually, I also have D8 and D32 helpers that are supposed to force 8-bit or 32-bit displacement. So I'll just create a couple of duplicate tests down here where these ones are tests for the D8 helper. And these ones are tests for the D32 helper. So in these cases for EVEX, we're just going to ignore Disp8 versus Disp32. And so these should just output the same things as the original test. Okay, so let's just go and take all of these and take them over to Encoder test. So let's do, let's maybe do it here. We'll say this is EVEX compressed Disp8. Okay. Let's just go and comment all of these. Right, so now I just need to take these. These are all going to be the ops. Then we're going to have some vector, which we're using k on. I think in all of these cases, so that's fine. Then we've got some memory access, which is cx, with some displacement. And so the displacement is always plus or minus let's just do this. Okay. Okay, let's just take the sign as well. So we'll go to D and put the displacement in there. We'll take out all these pluses. Okay, then we need NA, NA. So I think all of these are just two operand tests. So now let's just put the widths in. So this width is always x word. These ones here are y word. And then these ones here are z word. Then we've got the same things down here, so let's just go and take these. Then here we've got x word again. Then we've got y word. And we've got z word. Oh, these ones are, these top two are actually x word, these two are y word, and then we've got z word. And then these ones are the same thing. But in this case, we're going to use D32. And in this case, we're going to use D8. Okay, let's leave that how it is for now. So if we do a test here, could not match instruction for v add ps. Oh, add ps has 3 operands. So let's just go to these ones. All of these ones have 3 operands. So we'll put v1 in there. Get rid of this NA on the end. Okay, so now we get tests matching forms but outputting the wrong things. So for example, here we can see that we want 1, but I'm outputting 1, 0 for an actual 16. And then here we can see that it wants 127, but I'm outputting it as a disp32, like the raw number. So if we go to the form, I know what I need here is an element width. And what I need is a tuple as well. Maybe I'll just call this elem. And this one will be tuple type. So type, tuple type will be byte. Let's just do const. So we'll have tuple type, we'll have tuple NA, can be a tuple type of iota, so this will be the 0 value. Then the tuple types that I've got to implement right now are tuple full, tuple full mem, and tuple 1 scalar. Okay, so let's just go and do the test for that. So first we'll go to add ps. This will actually be v-add ps. So these ones are EVEX family, which is the only one that it actually applies to. And the tuple for this one was full. And in this case, we do need an element width as well. So the LM width for this is D word because it's a 32-bit float. And the way that I've set up the widths in this from the very beginning was to make sure that these, the enum, it basically represents the number of bytes. So byte is 1, word is 2, D word is 4, Q word is 8, etc., etc. That's why 0 is on the end here, is because I wanted it to not interfere with this width calculation. So we've got element for these ones, then we'll do the same for PD down here. So this one is also tuple full, but the elem here is actually Q-word. Another one that I did was mov SS. So for all of these EVEX ones, we need a tuple. And this was tuple1 scalar. So we'll have elem here is D word again, because it's a 32-bit element size. And then the other one that I did was DQ8. So for these ones, I think this one was full mem. Yeah. So this one is tuple of tuple full mem. And full mem is the only one that doesn't actually use an element size, so I don't need to put an element width in here. So let's just make sure there's no compilation errors. Undefined full. This should be tuple full. Okay, so now let's go to the encoder. And basically we're going to look for the disp checks. So here is where we set mod. This is where we need to decide whether it's disp8 or not. So if we do a switch here and say that if the form family is EVEX, then we're going to do something. Otherwise, if we've got the case, this case, which we're already doing here, then I think that's okay at the moment. If it's EVEX, okay, we'll just do this for now. So if it's EVEX, we'll just assume address indirects disp32. I guess this is actually going to be if there is a disp in the first place. Then we'll do the switch, which will be that if form family is EVEX, then we'll assume mod is disp32, but then we need to get the scale. So for example, we'll have scale is going to be a width, and we'll do a switch on the form tuple. So in the case that it's tuple full memory, then scale is just equal to the width of the vector that's being used to encode. If it's full, then we need to change depending on whether it's broadcast or not. So if RM is broadcast, then the scale is going to be equal to the form element width. Otherwise, it's going to be equal to the form. Otherwise, it's going to be equal to the width that was passed in. And then the other one that we've got is, maybe I'll put this one up here and this one down here. The other one that we've got is tuple1 scalar, in which case this is just going to be the element width. And then in default, we'll just panic and say unknown tuple type scale or something like this. And if we're in here, if we say that, for example, if form.tuple, I guess what we want to do here is say that if it's EVEX and form.tuple is not tuple NA. So we'll only try and encode this if we've actually got a tuple type to do a compare on. Then if the form tuple is not tuple full mem, and the form width has not been set, then we'll panic with tuple type. Let's say form is missing element width or something like that. Okay, and then what we'll do is say so now that we've got the scale, we can basically decide whether it's, we can try and find whether it's going to work as an encoding for compressed Disp8 or not. So in this case, we'll basically say that if disp mod int32 scale is equal to 0, then it's divisible, so we can at least try. Then we'll get the compressed disp8, which will just be disp divided by int32 scale. And then we want to just say if the compressed displacement fits within a signed integer, then mod equals disp8, and disp will actually equal compressed in this case. Otherwise, we just stick with disp32. Okay, so let's see. Oh, I think I need to update the tests to do the broadcast as well. So in here we've got a bunch of 1 to something tests. So in this case we'll do .b on the end. Okay, and that's the tests passing. So this does mean that if I don't add a tuple type or an element width to a form, then it will never use the compressed disp8 encoding, but I think that's okay. Okay, so this is just a quick addition to the end of the video, because I just realized that if I'm on a form where the family is EVEX, then I always need to take into account the compressed disp8 encoding. So in this case, I want to always just assume that it's going to be a 32-bit displacement and only do the potential compressed disp8 encoding if I've actually set the tuple type for the form. So that will avoid outputting incorrect disp8s for forms that I haven't set the tuple type for. So we just go test again just to make sure. And yeah, everything still passes.